All right, collision theory. So collision theory we have here in A levels is pretty much same to what we had back in IGCSE. If properly explained, there aren't much differences. If there are, they're very minor. They're not major. So in terms of collision theory, we can always come up with the explanation of effects of concentration, temperature, surface area, catalysts on the rate of reaction, even the pressure volume changes in gases. Now, collision theory states that in order to react with each other, particles must collide, and they must collide in the correct orientation and with sufficient energy. The word we have been using for the equivalent energy for both reactants and products as activation energy. Now, the particles may be atoms, the particle may be ions, molecules, or any other kind of species. The reactant particles must collide, they may simply bounce off each other with changing. This is known as ineffective collision. We have been calling it as unsuccessful collision, right? Ineffective collision takes place if the colliding particles don't have enough energy to react, which means they don't have the activation energy, which is the A part of the diagram. This whole is ineffective collision. As you can see, the hydrogen and the chlorine molecule is trying to react with one another. They're colliding, but they're still returning as hydrogen and chlorine molecules. And actually, no chemical reaction is taking place because it's an ineffective collision, and the combined energy of both of these molecules is less than the activation energy. Vice versa, if the collision is effective, that is known as the one in which the reactants are converted into products. So effective collision is the one shown in B. And this means that the combined energy of both of these molecules was either greater than or equal to the activation energy. All right. That's why they were able to return as products and not as reactant molecules. Okay. So this is pretty much the idea of kind of collision, the two kinds of collisions we have in accordance to collision theory. Now, the minimum energy that colliding particles must possess in order to be effective is known as activation energy. I've already explained that. So we already know for an exothermic reaction, this is the activation energy part, and this much is the difference between the reactants and products. We have been calling it delta H. This is usually downwards, and this is usually always upwards. Why? This is going to be positive every time. This may be negative in this case. All right. So moving on. In this case, endothermic activation energy is going to be the whole thing. That is very important. It's not just the part that consists of the bump. We can't say this much is activation energy. This whole thing is going to be the activation energy. And this can then be the change in delta H, which is going to be positive, of course. So even if I don't draw this and draw the straight line arrow upward, directed upward, that would be good. We're already done with this one too. So according to collision theory, a reaction will speed up if the frequency of collision increases or the proportion of particles with energy greater than the activation energy increases. The frequency of collision, or the number of collisions per unit time or number of collisions per unit second is something that we have considered a lot in discussing the speed of reaction or rate of reaction back in IGCSE. For this time, we are going to go with this specific thing. This is something which I can safely say is extra in A levels. So the proportion of particles with energy greater than the activation energy increases. Okay. So the catalyst is substance that increases the rate of reaction but remains chemically unchanged itself at the end of the reaction. So catalyst does this by making it possible for the particles to react for an alternate mechanism. This may be an alternate mechanism or a phrase like alternate route that we have been using back in IGCSE. So both of the terms are correct. Alternate mechanism has a lower activation energy. That's why we have been using the phrase that catalyst actually lowers the activation energy requirement for a reaction. So this is a pretty good diagram in order to explain that. The catalyzed reaction requires lesser amount of activation energy as compared to what the uncatalyzed reaction requires. In case both of the changes for delta H remains the same. It's just the height of the bump that changes. Okay, so that is a good way to show how catalyst reacts, or how catalyst acts actually in a chemical reaction. Now we do understand, and we have been using the definition: increases the rate of reactions chemically unchanged itself by the end of the reaction. That is understandable. But the other two definitions of alternate route and lower activation energy is also possible as a part of this definition, but only write it if the examiner specifically demands it. You do not need to extend your definition of catalyst, even if the question is not about it. I hope I'm clear. Can we move ahead if there are no problems with this one? All right. So the effect of concentration on rate of reaction. So remember that the increase in concentration of a reactant increases rate because it increases the frequency of collisions. So it is not enough to write there are more collisions. You must include an idea of collision per second. That's why the term frequency of numbers per second, or the frequency of collisions, is there. So that is a very important line. And for this line, I actually tend to take my students back on this specific point, because the frequency of collision has perfectly defined in these two lines, specifically this one. So the frequency of collision is number of collisions per unit time. You may take the unit per second, or if the discussion in that specific question is about per minute, you may take it as per minute. Okay, so that's why this important part. Now moving ahead, of course, we can define concentration or temperature or catalyst changes, all of those which we have been discussing in terms of frequency of collisions or collision theory. Starting off with concentration, we measure the concentration of solution in mole per decimeter cube. So the more concentrated the solution, the greater number of solute particles are there dissolved in a specific volume of solution. So more concentrated reactions have a faster rate of reaction. That's because the random motion of particles results in more frequent collisions. Since there are more particles, definitely there should be more number of collisions in there. So the frequency of collision increases. The effect of pressure in reactions involving gases is exactly similar to the effect of concentration in solution. So as we increase the pressure of reacting gases, there are more gas molecules in a squeezed space in a given volume. That has definitely been shrunken. If the pressure has increased, we have now a low volume. So in that shrunken space or squeezed space, we have more particles. So it's actually like the similar effect as we were discussing in concentration just a minute ago. So this results in more collisions in any given time and a faster rate of reaction. So I guess the diagram A and B clearly explains that the particles in box A are closer together than those in particle B. There are more particles in same volume, so the chances and frequency of collision uh, between reactical particles are increased. Therefore, the rate of reaction is greater in box A than in box B. So we can easily understand it. It means box A has higher concentration in terms of concentration. In terms of pressure, box A has higher pressure. So yeah, it is working in a similar way of giving us more rate of reaction. I hope that's clear. Is it?
Yes, sir.
Okay. So moving on, the effect of temperature on rate of reaction. Now, in order to fully understand rate of reaction, we need to look more closely at the energy possessed by reacting particles. This is something new. So far I was just teaching an explained version of what we studied back in A levels, but this thing over here, the Boltzmann distribution and this curve is something different. Make sure you understand it because you're going to find a lot of MCQs related to Boltzmann distribution. There aren't much paper 2 question, but definitely there are more MCQs related to this one. So in a sample of any substance at a given temperature, the particles will not all possess the same amount of energy. I usually tend to actually bifurcate it for my students. So instead of what we have here on the book, I'd like to give you an explanation in the background of what's happening. Whenever, let's say we have a liquid in a beaker, and let's say this liquid at a specific temperature, let's say 25 degrees centigrade, the students tend to understand that all the particles in the liquid have the same amount of kinetic energy. That's actually not true. Even if I don't talk about kinetic energy, if I simply use the word energy, a bigger broader term, even then that won't be true. Actually, the particles can be divided into three kinds of categories. Three categories. That is maximum energy particles, and then the medium or moderately energized particles, and then the minimum energy particles. Now, if these particles are supposed to go through a chemical reaction and if we convert it into products are reacting with something, then let me tell you, maximum energy particles are the particles which already have energy greater than the activation energy, so that their chances of being converted into a product because of a collision is or quite the highest. Minimum amount of energy particles, as the name suggests, is something the particles, the slowest kind of particles in this system, they don't have enough energy. They won't be able to go through the jump of activation energy, even if we provide them a little bit of energy. But these are the ones that are present inside the gray area. These are the ones which may jump over this bump and get on to the other side, be converted into products if they're given a good amount of energy. So the particles do not all possess the same amount of energy. A very few particles have a relatively small amount of energy. A few particles will have a relatively large amount of energy. This is the maximum energy particles I'm referring to. Most particles will have amount of energy somewhere in between. This is the bigger part. So this is a smaller portion. This is also a smaller portion. This one is the large portion, you can say. All right, so they are going to be converted into products really easily. They don't even need more energy. They don't even need a push. Minimum energy are not going to be converted into products even with a small push, since the push they require is much bigger than what we can have over here. Moderately energized are the ones in which we can provide them with a little bit of energy and they would be able to go over the hump. So that's a good kind of explanation as per Boltzmann distribution. The distribution of energies at a given temperature can be shown by this graph. Now, for this graph, I'm going to erase this. For this specific graph, this is the number of molecules and this is A activation. At and above this energy, the molecules will have enough energy to collide effectively. That means converted into products. So this shaded area shows the proportion of molecules in the sample that have the energy to cause a chemical reaction when they collide. And if you take a look of this whole thing, everything under this region, this counts as a very small portion of it, which can be converted into products. Now, Boltzmann gave us the idea of this distribution curve to let us know that a very small portion consists of this energy. And for the rest of it, we might be able to energize a smaller portion of it to be converted into products as well. So what happens is that the activation energy is already labeled in the shaded portion. We have seen activation energy is defined as the minimum energy required for the colliding particles to react effectively, be converted into products. So when we raise the temperature of a reaction, the average kinetic energy of the particle increases. So what happens when we increase the temperature? So particles in solution and gases will move around more quickly at a higher temperature, resulting in more frequent collisions. Actually, to be honest, more effective collisions for a specific region. Now, take a look. This is the previous graph we were talking about at a specific temperature. Let's say we just increase the temperature by 10 degrees centigrade. This is T plus 10. This is what is going to happen over here. Imagine we have the same shaded area, but this time, since we have a new graph, the number of molecules with the maximum energy or the maximum value are going to stay in this portion. And now there is a bigger portion which is going to be converted upon effective collisions into products. Okay, so particles, these experiments show us that the effect of temperature on rate of reaction cannot be totally explained by frequent collisions. The key factor is the proportion of successful collisions increases greatly as we increase the temperature. And just 10 degrees centigrade is a very good way of showing it. Now, distribution of molecular energies changes as we raise the temperature. Boltzmann distribution shows us that at a higher temperature, the peak flattens and shifts to right, giving us a bigger portion of the particles capable of being converted into products. Why? Because they have the cumulative energy equal to or greater than the activation energy. Now you can see the difference between the previous graph, which is this much of it, and the current graph, which is actually a bigger portion converted into products. Do you get the idea?
Yes, sir.
Okay. A very common question in past papers is what happens if you increase it by 20 degrees centigrade and not by 10 degrees centigrade? So, can any one of you try to do it? I've already turned on the annotation, so it's fine. You can go ahead and take a guess. Any one of you. Would you like to draw it over here? Come on, it's easy. Try it. Do you understand what I'm talking about? Do you understand my question?
Sir, could you repeat your question?
I'm asking you to draw a curve, a sample curve. You can already see the t degree centigrade curve and t plus 10 degree centigrade curve, right? So it should be easier for you to draw t plus 20 degree centigrade curve, right? I hope you can try it. One of you can. Use different colors, try it. Actually, both of you can draw at the same time. I don't mind. Go ahead, give it a shot.
It will be more towards the left, towards the right.
Exactly. Now, if you already understand it, then you can take a shot at it. Go ahead, draw it. You already have the annotations on, so this should not be a problem. Both of you can try. Ali, I guess you understand this part too, right?
Yeah.
Then go ahead, give it a try. Remember, in T plus 20, you have even a bigger portion of molecules having a greater proportion of energy, having a greater proportion of molecules having the energy. A good try. What if I want you to extend this line as well? Can you see this line? Can you extend this line for your own graph, please?
Yeah.
Good try. So I guess that's actually a correct shot at it. So I guess you both understand that now we even have a bigger portion of it. But if you give it a couple of tries, you would understand and see the temperature has an effect to an optimum position. I mean, you can draw a graph for 10 plus 20, 10 plus 30, maybe 10 plus 40, maybe a couple of tens of degrees centigrades more, but how much are you going to add to it? Ultimately, this would become something that won't bring a bigger change, right?
Yeah.
From drawing this, what I wanted you to understand, everyone can draw a 10 plus 20. You can even give a 10 plus 30 a shot too. But I hope you understand there is a limit for flattening the curve every time a little bit. And after some time, you are going to flatten the curve up, maybe up to this point. What good is that going to do? Actually, nothing in terms of change. So after a couple of times, maybe after 4 to 5 times, you won't be able to draw a curve that has a bigger set of molecules which can go through effective collisions, be converted into products. So the point I'm trying to make by drawing these curves is to give you the idea that temperature can have a very good effect on rate of reaction. And as we are saying that it is doubling for just a 10 degrees difference, maybe it would triple for a 20 degrees difference, maybe 4 times for a 30 degrees difference, but that won't keep on doing that. Let's say we increase it 1,000 times. Can we affect a 10,000 times a difference in the frequency of the colliding particles for effective collision? That's actually not true. So temperature is going to have this effect to an optimum, which is going to slowly fade and which is slowly going to not show you a bigger change after the rise in temperature. I hope you get the point, right?
Yes, sir.
Good, good. The whole sole purpose of drawing these curves was to give you an idea that this all is progressive, but to an optimal range. After that range, this progression actually does not bring you much of a difference. So therefore, increasing the temperature increases the rate of reaction. That's because the increased energy results in particle moving around more quickly. This increases the frequency of collision, also the proportion of successful collisions. Those that result in a reaction, reactants converted into products increases because the proportion of particles increasing the activation energy also increases. This is the more important factor. This is the more important factor. Keep this specific line in mind. That Boltzmann distribution is more important when it comes to change in temperature, increasing the rate of reaction. It's not just about the frequency of collision, because you might increase the frequency of collision by a little bit, but if their activation energy is not greater, their combined energy is not equal to or greater than the activation energy, increasing the frequency of collision sometimes may not help alone, right? Do you get the point? By the more important factor?
Can you repeat it?
Okay, let me give you an example. Instead of repeating, I think an example can work greatly over here. Now you both know that air is composed of two main gases for 99% of its whole volume. Now, nitrogen contributes most to the air around us, and oxygen comes at second for this contribution. These both gases actually do not normally react in air. They don't form any products, but when they do, the product is this, right? Now, this reaction happens at about 3,000 degrees centigrade, which is pretty high of a temperature, right? Now, in order to make my point, let's say I do not increase it to 3,000 degrees centigrade. I'm gonna simply increase it to 300 degrees centigrade. Now, when I increase it to 300 degrees centigrade, does that give me the product from nitrogen and oxygen? Probably not. Increasing it to 300 degrees centigrade from the room temperature of, let's say, 25 degrees centigrade, I increased it to 300 degrees centigrade. I would definitely increase the energy of many particles. They will go around more quickly. Many molecules of nitrogen and oxygen will grow around more quickly, and they would even collide with each other with more frequency. Means the number of collisions between nitrogen and oxygen particles, let's say at room temperature, there were, let's say, about 100 collisions. All right, I'm just trying to use some numbers, some made up numbers to explain myself. Now, this is an increase, we can say 12 times increase. So there may now be 1,200 collisions per minute, right? Do you get my point? But does that convert my nitrogen and oxygen into a no? No, it won't.
No.
Why? Because still the particles will not have a combined energy equal to or greater than activation energy. The proportion of successful collisions will still be negligible until unless I get somewhere closer to 3,000 degrees centigrade, which is my requirement. So this is the more important factor. Sometimes we can give them a little bit of energy boost, and sometimes we can really increase the frequency of collisions. But are those collisions going to be successful or effective collisions every time? No, that might not actually be true. So that might only be attained when we are going to go at least equivalent or more than the activation energy, which is only going to be the case closer to our actual requirement. Make sense?
Yes, sir.
I hope now it makes more sense, right?
Yeah.
Great. So if that makes sense, you can easily let yourself through many MCQs with a correct answer instead of falling for a temptative wrong answer. Because sometimes they tend to do MCQs like this. Sometimes they use this very thing to make students fall for a wrong option. That option may be very tempting, but that won't be correct, because just increasing the frequency of collisions might not get you a lot of product. Remember, the second factor is the more important factor. Now remember that increasing temperature increases the rate of reaction because of two factors. So frequency of effective collisions is greater because the greater kinetic energy of the molecules, or a greater proportion, have kinetic energy greater than the activation energy of the combined effect. The second reason has a far greater effect. He is actually explaining the same thing again. This time it's just that instead of using just the word energy, he's using the term kinetic energy. So whether you use the bigger, broader term, just the energy term, or use the exact kinetic energy term, it does not matter, because both of them are actually explaining the same thing. There are two factors, and the second factor is more important and has a far greater effect than the first factor. And I think I've already explained it clearly, so let's move ahead. 9.4, catalysis. Now, catalysis means a reaction in which a catalyst has been used. Catalysts actually play its important part, increase the rate of reaction, and actually helped us to go with the reaction by a different pathway, a different mechanism, maybe lower activation energy, maybe by an alternate route than as compared to the uncatalyzed reaction, and actually was helpful. That kind of reaction would be considered as catalysis. Now, if we talk about again the Boltzmann distribution curve, and we discuss the effect of using a catalyst as compared to an uncatalyzed reaction, this is how we're going to look at it. Okay, now this is very much different to what happened in temperature. Temperature was actually trying to flatten the curve with giving us more molecules over there. But catalysis is behaving a little bit differently. It's actually taking the whole category, or the number of this line, which actually was representing the molecules who had the combined energy greater than the activation energy. It's actually taking the line back a few more notches. And those few more notches is actually working a great effect on the whole reaction. Okay, let's go with the words that are written in the book. Note that the presence of catalyst does not affect the shape of Boltzmann distribution. A very important point. However, providing a lower activation energy, a greater proportion of molecules in the reaction mixture have the sufficient energy to react. Okay, now let me give you an example by actually taking about this curve. Let's say a school has 1,000 students. Okay, and that school announces a sudden trip. Let's say the trip is some kind of international trip, right? And the fee for that trip is actually set at, let's say about 4,000 US dollars. Okay, so a very small portion of those students would afford $4,000. I'm talking like a Pakistani student. I'm not talking like Arabian schools. Since in Arabian schools, most of the students actually are capable of paying those amounts and can actually go through over the curve. So not talking about as a traffic person, totally talking about as a Pakistani. Okay, a very small percentage of students would be capable of paying that fee and going for an international trip, and that actually happens in every school too. If a school has a strength of 1,000 students, you would see that for an international trip, not all 1,000 would be willing to go and pay the fees and taking the whole initiative. Only a few students do. Now, what if the school in the last days of finalizing the student bring it down to 2,500 US dollars? Now, many more students which were actually capable of affording this were previously saying no because of this 4,000, and just bringing the bar a few notches back or bringing it down in terms of activation energy allows a lot more students to go for that trip. In the similar way, for molecules to be capable of going through the hump, going over the hump, going for an effective collision, and actually becoming from reactants to products. Make sense?
Yes, sir.
So even if the energy requirement is lowered, and that's why we have been using the lower activation energy term for the definition of catalyst. Now, I hope you now understand what this lower energy requirement for using a catalyst means. This is what it means. This is how more number of molecules or more particles now have the energy greater than or equal to the catalyst's activation energy. And this is how we actually denote it. Now, they can be a part of those molecules which are capable of being converted into product. Right? That's how uncatalyzed and catalyzed reactions bring a difference between one another. I hope I make myself clear. I hope the whole graph is clear too. Okay?
Yes, sir.
Now, when you are about to write or draw something like this, these words or this way of representing is very important. You can represent it like this, or you may also represent it like this, uncat. Okay? And represent the other one as cat. You can even do it for answers which have a case scenario involved, a case story in which a catalyst has been used. So this would be good enough to tell the examiner that you are not talking about the activation energy for a reaction in which a catalyst is under use. This is a good way of writing it. And this is a generic bigger broader term, and this specific shows about the activation energy for an uncatalyzed reaction, specifically telling the examiner that you want to talk about a case in which catalyst is not going to be used. All right. So you can exactly use the same symbol in exams to answer your questions. Now, catalysis is of two types, homogeneous and heterogeneous. This heading is homogeneous and heterogeneous catalysts. This heading can also be homogeneous and heterogeneous catalysis. Okay, so whether you write it as catalyst or whether you write it as catalysis, both are going to make sense. And since on the next page you are going to face both homogeneous catalyst terms and homogeneous or heterogeneous catalysis terms. Now, when a catalyst and reactants in a catalyzed reaction are in the same phase, for example, they are all solid, for example, they are all liquid, for example, they are all solutions, this is the way we can define it as homogeneous catalyst. Catalyst as homogeneous if it is dissolved in water and the reactants are also present in aqueous solution. If a catalyst is present in different phase to the reactants, we call it a heterogeneous catalyst, and probably the catalysis is heterogeneous catalysis. For example, for hydrogen peroxide being converted into water and oxygen, the reaction commonly used as this. The catalyst, if that is going to be manganese 4 oxide powder, it is heterogeneous catalysis. All right, since this is an insoluble solid and that does not dissolve. Okay, so many heterogeneous, there are examples for heterogeneous and homogeneous catalysis. You won't have a problem. This book is filled with examples, even if the examples are not on these pages. Now, many heterogeneous catalysts are solids and can catalyze gaseous reactants. These reactions take place at the surface of a solid catalyst. Let me clarify. We have been talking about in O levels or IGCSE, the Haber's process, nitrogen and hydrogen reacting and producing ammonia. We have been talking about the catalyst pure iron or finely divided iron. Now, the iron in the gases are the example of heterogeneous catalyst or heterogeneous catalysis, right? So this kind of iron for ammonia from nitrogen and hydrogen or nickel, when we are adding hydrogen gas to vegetable oils to making margarine, these are all examples of heterogeneous catalysis. Okay. So for heterogeneous catalysis, oh, we're done with the chapter. Thought there is something next added to it. I guess there was, but it now probably has been taken out of the course, maybe. So yeah, we are done with the chapter.